All right, let's get started. Okay, so hello everyone, this is SeungryongKim. So today we will continue lecture note 10, lecture 10. So in this lecture note, we discussed what orthogonal fraction is and what Gram-Schmidt process is, right? So because our previous lecture was the recorded video, was substituted by the recorded video. So today I will just briefly review what we've done. Yeah, no. Let me start from here. All right. So last week we discussed what best approximation theorem is. So it was the theorem 9. So the theorem say that if we have a subspace W in Rn space and let Y be any vectors in Rn space, for example, maybe Y lies in the outside of the subspace W, maybe here, looks like this, then Y hat be the orthogonal projection of the Y onto W here. So then Y hat was the closest point in W space to the Y vector Y in the sense that Y minus Y hat, the length of the Y minus Y hat is smaller than Y minus length of the Y minus V, where the V is the arbitrary vector in the W space. In other words, W hat is the closest point from the Y to subspace W. It was the best approximation theorem. So, in other words, the vector Y hat is called the best approximation to the Y by the element of the W. The distance from the Y to V given by the length of the Y minus V can be regarded as error. So this theorem say that this error is minimized when V is equal to Y hat. So V is the closest point. That's the best approximation theorem. And yeah, that's it. So we already discussed why you have to know this, right? So we want to find out the approximate solution for the inconsistent system. So we will discuss this one in chapter 6.4, but here we just mention the closest point can be determined by orthogonal projection of Y onto the W space. So say W. Right, so we already proved this theorem here. And we also discussed the property of the orthogonal projection. So yeah, here. We also discussed also normal basis, not orthogonal basis, also normal basis, by simply normalizing the each orthogonal basis to become a length 1, looks like this. We can derive this orthonormal basis math equation, looks like this, which can be summarized as a projection of the matrix vector Y to subspace W is equal to Y transpose U transpose Y for all Y in Rn space. This is a theorem 10. Right, that's it. And in lecture note 10, we started to discuss the Gram-Schmidt process. So it was a chapter 6.4. Yeah. So here we just recap orthogonal projection and orthogonal complement, or the also component of Y orthogonal to W, like this. In this case, Y can be decomposed as a Y hat plus Z. Vector Y hat is called the orthogonal projection of Y onto W. Vector Z is called the component of the Y orthogonal to W. Depends like this. And we started the Gram-Schmidt process, which is a simple algorithm for producing the orthogonal or the orthonormal basis for any non-zero subspace of Rn space. Orthogonal and orthonormal basis are exactly the same, except for this is just a normalized version of this orthogonal basis. So here was the example for your subspace W, which was spanned by vector xn, x1 and x2. x1 is here, x2 is here. First of all, x1 and x2 were basis for the subspace W. Then the question is constructing an orthogonal basis V1 and V2 for subspace W. So we have to find out orthogonal basis. 그렇죠? How to find this? Our strategy looks like this. So here is the vector x1 and x1 and vector x2. These two vector is inherently not orthogonal, right? So our strategy is like that. So first of all, we just set v1 as x1, and then we want to find the v2, which is orthogonal to the v1. Then we want to make v1 and v2 as an orthogonal basis for the subspace W. This is our strategy. Okay. Then how can you do that? Because we already know v1 is equal to x1, so we have to find out v2. We already know v2 is the orthogonal component of the orthogonal complement of the x2, orthogonal to v1, x1. 그래서 orthogonal 컴포넌트를 찾는 거였고요. 뭐였어요? x2 마이너스 x2에서 이거 orthogonal fraction p를 빼주니까 이렇게 식이 나왔고 쭉쭉 계산해보면 0, 0, 2. So in this case, v1 and v2. v1 was 360 and v2 was 002. And v1 and v2. The set of the v1 and v2 is an orthogonal basis for the subspace W. This is our main strategy. Today, we will generalize this strategy to find out arbitrary orthogonal basis for arbitrary subspace W. This is the exactly Gram-Schmidt process. Before that, question. By the way, all of you already took the previous recorded video lecture, right? Is there anyone who did not take a recorded video yet? Did not take a previous lecture yet? 여러분들 다 했을 것 같은데 혹시 저번 시간 안 들은 친구 없죠? 네. 그러면 question so far. Question? No? Any other question? Nope. Okay. Right. Today, let's move to the more advanced one. I mean, the more difficult one. Let's suppose that we have a 3 vectors in our post space. Vector x1 is 1, 1, 1, 1. X2 is 0, 1, 1, 1, 1. X3 is 0, 0, 1, 1. Then x1, x2, and x3 is clearly linearly dependent, right? So one of the vector cannot be represented by linear combination of the other vectors, so they are linearly dependent in this case, right? Thus, it is the basis for arbitrary subspace W defined in our post space. Because this is the linear, the set of these vectors are linearly dependent, so it's going to be the basis for the arbitrary subspace W. The question is construct an orthogonal basis for subspace W. This is the problem. In other words, orthogonal basis for subspace W means the orthogonal basis, I mean the new vector v1, v2, v3. For the set of the new vector v1 and v2 and v3, any vector, let's say y, any vector in W space should be defined by a linear combination of the v1 and v2 and v3, and they are v1 and v2 or v3 should be orthogonal each other. This is the our main objective that we have to solve here. Let's do that. So, first of all, in step 1, let's assume that v1 is equal to x1. v1 is equal to x1. So let me draw first. Let's suppose that we have 3 arbitrary vectors, x1, x2 and x3. Then first of all, we want to set V1 as a x1 itself. x1 itself. Then in this case, W1 spanned by x1 is just spanned by V1 because x1 is equal to V1. So this W space is just the line defined looks like this. This line is W1. In step 2, we have to find out V2. Let V2 be the vectors produced by subtracting from the x2 its projection onto the subspace W1. It means that, okay, let me draw again. It means that we have to find out this vector. This vector V2 become x2 minus p. P was also a projection of x2 onto W1. Then V1 and V2 will be also know why V1 and V2 can represent any vector spanned by x1 and x2. So x1 and x2 and V1 and V2 can be the basis for the same subspace W, right? So this is our next strategy. So V2 is equal to x2 minus fraction of V1 onto W1 space. So how can I solve this one? How can I compute this one? Also one fraction of the V1 onto W1. By just definition, V1, it can be x2 inner product V1 over V1 product V1 times V1. So we already know x1 and x2. x2 was 0, 0, 1, 1, 1, and we already know V1 was x1, 그쵸? 1, 1, 1, 1. Then you can easily compute this one, x2 minus x2, V1 inner product V1. So let's do that. First of all, x2 was 0, 1, 1, 1. 그쵸? Then x2 inner product V1 is going to be 1 square plus 1 square plus 1 square. It's going to be 3. This one it's going to be scale 1, 24. Then V1 was 0, 1, 1, 1, 1. Then it's going to be V1, it's going to be negative 3 over 4, 1 over 4, 1 over 4, 1 over 4. So in this case, V2 is the component of the x2, component of the x2 also equal to x1. Component of x2 also equal to x1. And V1 and V2, set of the V1 and V2 is an orthogonal basis for subspace W spanned by x1 and x2. In other words, if we consider the subspace spanned by W1 x1 and x2, it may be this space. Then V1 and V2 can represent this subspace W spanned by x1 and x2. So V1 and V2 is an orthogonal basis. So this is the one. In this case, the subspace was line. In this case, subspace was plane. Maybe in next time, subspace will be the it's not a plane anymore. It may be the defined in 3D space, 그렇죠? Maybe defined in 3D space, but this is just the extension from the 1D to the 2D plane, 그렇죠? Anyway, this plane was W2, which is spanned by x1 and x2, and v1 and v2. So from x1 and x2, we already found v1 and v2, which are also on each other, right? Next step is we have to find out new vector v3. Maybe it should be orthogonal to the v1 and v2. Maybe aptly x3, I mean the v3 should be orthogonal to the subspace W2. Then v1 and v2 and v3 can be the orthogonal basis for the arbitrary subspace W. Right. So let's do that. So before that, in step 2, optionally, if appropriate, scale v2 to simplify later computation. 그래서 because the v2 is hard to use, I mean the difficult to use, so we just normalize v2 as a v prime, which is the -3, 1, 1, 1 for simplifying the later computation. Finally, in step 3, we have to find out v3. Let v3 be the vectors produced by subtracting from the x3 each projection onto the subspace W2. So in other words, let's read through again. We already have the W2 spanned by v1 and v2. Then we have a vector x3. Then we have to find out vector v3 by subtracting the x3, each projection onto x3 each projection onto substrate v2. 그래서 이 프로젝션을 찾아서 빼주면 v3가 나온다라는 거죠. Then we have to compute this one, which is equal to projection of x3 onto the W2 space. W2 is spanned by v1 and v2 frame. 그렇죠? Arbitrary basis. Then this one, fraction of the x3 onto the W2 space, it's going to be the x3 inner product v1 over v1 inner product v1 times v1 plus x3 inner product v2 prime over v2 prime over v2 prime and v2 prime. This is just the equation. 그렇죠? You don't need to memorize this one, but we will just use this equation. 그렇죠? 외울 필요 없어요. 여러분 이 equation 가져오면 돼요. 그렇죠? Then in here we already know x2, x3, v1, x3, v2 prime. Then you can easily find this one. Please try to derive this one yourself. As we already know in your midterm exam, you have to practice. You have to study to solve this kind of equation yourself, because you are not allowed to use the calculator or any other one. So please try to solve yourself in your homework, then which will help to expedite your solution skill. 그렇죠? Anyway, it's going to be the 제로 2 over 3, 2 over 3, 2 over 3, 2 over 3. Then, because of v3 was x3 minus fraction of x3 onto w2. 그래서 x3에서 요 fraction x2 over w2를 빼주는 거니까 we already know x3. 그렇죠? What was that? x3 was 0, 0, 1. 그렇죠? 0, 0, 1. 0, 0, 1, 1. Then 0, 0, 1, 1 minus here 0, 2 over 3, 2 over 3, 2 over 3. So v3 is gonna be 0, negative 2 over 3, 1 over 3, 1 over 3, 1 over 3. Then if we draw this one again, v1 and v1 2 prime here, and this is the W2 spanned by V1 and V2 prime, and X3 was the outside this substrate W2, and this point is the projection of the X2 onto the W2 space. Looks like this. Then finally, V3 is going to be the X3 minus projection of the X2 onto W2. Okay, V3 is going to be X3 minus projection of X3 onto W2. And finally, we got a V1, V2 prime, V3. V1, V2, V3. In other words, we got V1, V2 prime, and V3, which is going to be orthogonal projection, orthogonal basis for substrate W spanned by vector x1 and x2 and x3, where x1 and x2 and x3 was not orthogonal, but in this case V1 and V2 prime and V3 is going to be the orthogonal, so it's going to be orthogonal basis for the arbitrary substrate W. That's exactly Gram-Schmidt process. You can find out arbitrary orthogonal basis from the basis vectors for the arbitrary substrate W. This is Gram-Schmidt process. It's very, very easy, right? And very, very intuitive. That's the point. Question or comment or whatever. Please give me your comment. So, are you clear to understand so far? 자, 여러분 혹시 여기까지 이제 우리가 많이 왔는데 뒤에는 이제 거의 그램-슈미스를 한번 정리하는 걸 거예요. 그래서 자, 혹시 여기까지 이제 왔는데 조금 어렵거나 이해가 안 되거나 하는 친구들, 또는 이해가 잘 되는 자, 이해가 됐습니다 하는 친구들 한번 좀 의견 좀 줄까요? 어때요? 다 축제 갔나? 축제, 컴과 축제 내일 아니에요, 여러분? 컴과 주점 내일로 알고 있는데. 그쵸? 저희도 갈 거예요. 교수님들 몇 분 가실 건데 혹시 맞아? 혹시 내일 주점 오는 친구들 혹시 보고 인사해줘요. 알았죠? 혹시 제가 못 알아보면. 자, 근데 이거 자 의견 좀 줘봅시다. 누가 있죠? 맨날 답변 잘하는 친구. 예담, 형민. 자, 형민 학생 질문 있었고 다른 친구들 혹시 또 역시 예담. 오케이. 다른 친구들 정우 학생 질문. 자, 형민부터 갈게요. So the question was question by 형민 was where Gram-Schmidt process can be used, right? So there's so many kinds of the computer algorithm that can benefit from the Gram-Schmidt process. The first one is that, okay, so let's go back to our lecture note 9. So here. So we already discussed here. So we already discussed our next step is we want to find out approximated solution for this kind of inconsistent system, right? So Gram-Schmidt process, which attempts to extract the orthogonal basis, can be used to solve this closest point, which will be discussed in in chapter 6.5 next week, maybe next week. Not next week, maybe this Thursday. So that's the one of the application. Another application is maybe next week we will talk about another factorization technique, eigenvalue decomposition or eigen factorization, where we can use this Gram-Schmidt process to derive eigenvalue factorization technique. Okay. And others. 정우? The reason is here, optionally, we just normalize V2 as a V2 prime for the to simplify the later computation. But you can do same things by using the V2. Maybe then V3 may be different because we start from the different V2, different V2, because the orthogonal basis is not unique, right? So you can use the V2, but we just use V2 prime for the simplifying, the later computation. Okay. Any other question? Either student, 형민, 예담, 정웅 말고 맨날 대답한 친구들 말고 다른 친구들. Okay, so when I checked our calendar, maybe we just have the 3 weeks left before the final exam. So that's going to be the end of this semester. So if you have difficulty in understanding so far, please let me know now. Clear? 우리가 아마 좀 지금 진도가 조금 빨라서 뭐 제가 사실 뭐 천천히 좀 가도 되는데 여러분들 어느 정도 이해하는지를 좀 보면서 가고 싶어서 그러는 거라. 혹시 뭐 어려운 친구들 괜찮죠? 한 학생. 자, 90명 중에 5명이 괜찮으면 괜찮겠죠? 자, other question or the question from the foreigner student? No? Right. So this is the Gram-Schmidt process. Observe that V3 in double space. Double space mean spanned by original vectors V1, x1, x2, x3. Because x3 and projection of the x3 onto W2 are both in linear combination of the x1, x2, and x3, which span W. So V3 is also in double subspace W. So V1, V2 prime, V3 is an orthogonal set of the non-zero vectors in W space has a linear independent set in W. Because they are orthogonal set, so they are independent, 그렇죠? which was equivalent, 그렇죠? orthogonal set과 linear independent은 그 뭐였어요? 그 equivalent 했죠? 그렇죠? Note that subset W is three-dimensional. Subset W is three-dimensional since it is spanned by linear independent set x1, x2, and x3. 그렇죠? Dimensionally, 그렇죠? We already discussed dimensionally in the chapter lecture 9. 맞죠? lecture 9 dimensionally. 아니죠. lecture we'll discuss here. We already discussed this one. This dimensional concept in lecture 6죠. 7. 그렇죠? 7에서 했었고요. Anyway, by the basis theorem in chapter 2.9, basis theorem, V1, V2 prime, V3 is going to be the orthogonal basis for the subspace W. So please check the basis theorem in section chapter 2.9. So we discuss if if V1, V2 prime, V3 is orthogonal basis, then and linearly orthogonal each other and linearly independent, and V1, V2 prime, V3 is orthogonal basis for the W. So this one, we found this set V1, V2 prime, V3. This is Gram-Schmidt. Right. Let's summarize Gram-Schmidt process, or let's generalize Gram-Schmidt process. Something looks like this. Use the theorem 11. Given a basis x1, x2, and xp for a non-zero subspace W of Rn space, we want to find out we want to find the orthogonal basis V1 and V2 and VP. V1 and V2 and VP. V1 and V2 and VP. Then we can do similar step that we discussed in the 뭐예요 이거? example 2. 그렇죠? We can do this one in general. Here. So first of all, let V2 V1 as x1. Then define subspace W1 by V1, which was just line. Then we compute the V2, which is x2 minus fraction of the x2. Let me write again. Fraction of x2 onto the W1. Then which is defined looks like this. And we can think W2 spanned by V1 and V2. 그렇죠? Then V3, it's going to be the x3 minus 뭐예요? x3 minus fraction of x3 onto W2. 그렇죠? W2, which was spanned by V1 and V2. Then which is equal to x3 minus the fraction of x3 onto the W2, which is going to be, this looks like this, 그렇죠? Like this. x3 in the product of V1, V1 is product in V1 in the V1 minus x3 in the product of V2 over V2 is in the product of V2 times V2. Blah 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 blah. Finally, given the previous subspace, which is going to be the maybe WP minus 1, then we can find out VP, which is equal to x2 minus fraction of the xp onto WP minus 1, which can be divided like this. So xp, for the xp, we have to consider V1, V2, VP minus 1. Then it's going to be the VP. Then we can say that orthogonal basis V1, V2, V3, VP for subspace W, which is spanned by original basis V1, V2, and VP. That's the Gram-Schmidt process. That's the Gram-Schmidt process. Question? Very clear, right? So it's very, very clear. Then V1, V2, VP is an orthogonal basis for the subspace W. In addition, span V1, V2, VP is equal to span x1, x2, xp for one k is equal to greater than and equals 1 and smaller than and smaller and equals to p. Looks like this. In other words, this one V1 is spanned by x1, which is spanned by V1, electricity, and W2 is spanned by V1 and V2, and which is spanned by x1 and x2. Similarly, we can derive this one. So span V1 to Vk is equal to span x1 and xk. Okay, so we will skip this proof because we easily understand it from the previous example. 그렇죠? 여기 example랑 똑같이 푸는 거예요. 그냥 이거를 표현한 것 뿐인 거야. 그렇죠? So we will skip proof this one. So this is the Gram-Schmidt process. one more thing is that by using the Gram-Schmidt process, we can find out also gonal basis, right? But in some application, we may need also normal basis. So also normal basis can be easily constructed by from an orthogonal basis by Gram-Schmidt process, right? How? By simply normalizing, that is scaling for whole vector vk to what? To 0, to 1. So we can just normalize each vector v1 and v2 and vp as a u1, u2, and up to make each length of each vector 1. Then we can achieve also normal basis. That's also normal basis. Let me show you example. You can easily do that. Previous example construct also gonal basis v1 was 306, v2 002. Then also normal basis can be determined by u1 and u2, which is u1 is equal to v1 over length of the v1. So normalize, 그렇죠? normalization으로 합시다. Then which is going to be 1 over square root of 5, 2 over square root of 5, 0. u2 similarly it's going to be 0, 0, 1. So orthogonal basis is going to be u1 and u2. Okay, that's the way to achieve the orthonormal basis. COSE111. 질문? 다 이해했죠? question? 질문? yeah. No more question, right? So if we draw also normal basis here, also normal vector, also normal set can be defined like u1, u2. If length of the v1, v2 prime, v3 is larger than the 1, then we can draw looks like this: u1, u2, and u3, and they are orthogonal each other. This is also normal basis for the substrate W. After substrate W spanned by x1, x2, and x3. That's it. No more question. By the way, today we will distribute homework maybe 5인가? Homework 6, 그쵸? Homework 6, which will cover by this chapter 6.4. So please remember. Question. If there's no more question today, let's finish curve factorization. Let's move to the next topic. So by using the Gram-Schmidt process, so similar to the Hyungmin's question, by using the Gram-Schmidt process, we will derive one more factorization technique, right? So first of all, which factorization we discuss in midterm exam? Which factorization? What's that? LU, 그쵸? So it was just LU factorization. So today, by using the Gram-Schmidt process, we will introduce more advanced factorization, QR factorization. Now let's compare this QR factorization to the LU factorization. Okay, all right. So QR factorization is like that. So QR factorization is the exact the QR factorization is very similar to the Gram-Schmidt process. It resembles the Gram-Schmidt process. Yeah. So if vector A is an m by m matrix with linearly independent columns, there was one constraint. So we have a vector matrix A, m by n matrix, and we just assume that each vectors, each column vectors are linearly independent. Then matrix A can be factorized as QR, not a LU, QR, where Q is an m by m matrix, whose columns form a also normal basis for the column space column space A. So QR means Q. So the matrix Q is going to be the m by n, and each column vectors orthogonal basis for column space of matrix A, column space of matrix A, and R, which is in n by n space. It should be n by R, matrix R is an n by n upper triangle. Looks like this, 그죠? Upper triangle inverter matrix with positive entry on each diagonal. It should be looks like this, and there should be positive entry on each diagonal. So this value, each value should be positive. This is the QR factorization. In other words, any arbitrary matrix A with a linear independent columns, then it can be factorized the Q and R. Where Q is an m by n matrix whose columns form a also normal basis for a column space of matrix A, and R is an n by n upper triangle inverter matrix with a positive entries on each diagonal. This is the QR factorization. Sorry about that. Also normal, 그렇죠? Also normal basis, 그렇죠? 이거 also 고나로 써 있구나. 죄송합니다. Also normal, 그렇죠? Normal, 그렇죠? Also basic word complex. This is the QR factorization. So, first of all, let's think about how to factorize QR from the matrix A first, and let's talk about how to use this QR factorization to solve and understand your matrixification, Ax equals B. Okay? So, first of all, let's prove the existence of this Q and R, and let's talk about how to derive matrix Q and matrix R. Define looks like this. 그렇죠? This is the QR factorization. Question so far? No? All right. So first of all, it's just enough to show how we can construct the Q and R in a way specified this theorem. So here's how. So it means that here we won't prove whole the theorem, but we will just show, we will just see how to construct the Q and R. Then that's the way to prove this theorem. 그렇죠? 이제 여기에서는 이 theorem을 뭐 진짜 정말 제대로 증명하려면 너무너무 어렵기 때문에 그게 아니라 우리는 어떻게 Q와 R을 구하는지를 얘기하면 바로 이제 요렇게 나오는지 정말 Q와 R이 이렇게 나오는지를 한번 얘기를 해보려고 하는 거예요. 알겠죠? So let's assume we have a matrix A which is consisting of the column vector x1, x2, xn. Then let's find the Q and R. Q and R. So first of all, in step 1, which is designed for constructing matrix Q, construction matrix Q. So first of all, columns of matrix A form a basis for the column space of matrix A. This is the definition of the column space since they are linearly independent. So because the columns of matrix A already linearly independent, the columns of matrix A themselves form a basis for the column space. Then Q here. Each column vectors in Q is going to also normal basis for the column space A. It means that the question can be reformulated by finding also normal vectors from the X vector, column vectors for the matrix A. We already know how to do this, right? By using the Graham-Schmidt process. That's the way to use Graham-Schmidt process to derive factorization. In other words, let these columns, I mean the columns of the matrix A be x1, x2, and xn here. Then we can construct the also normal basis u1, u2, and un for the column space A by Graham-Schmidt process. We already know, 그렇죠? We already discussed. Using this basis, we can construct the Q, which is u1, u2, and un, because they are also normal basis. 그렇죠? So we found Q. This is a step 1. In step 2, we have to construct R. Construction of R. So we already discussed how to construct the Q. Then we have to construct how to construct R. This is step 2. So for K from 1 to the n, each xk, x1, x2, and xp, xn is spanned by x1, x2, and xk. So spanned by the previous vectors, 그쵸? x1, x2, and xk. We already know this is the spanned by u1 and u2 and uk. 그쵸? From where? From the here. 그쵸? Graham-Schmidt definition. This one. We already know, right? Therefore, there exists constant value or 1k or kk such that xk, arbitrary vector xk, column vectors, one of the column vectors k can be represented by linear combination of u1, u2, up, and uk. Looks like this linear combination of u1, u2, uk from this pact, 그렇죠? Then maybe there exists the uk plus 1 by un, but we just assume that it's multiplied by the 0 because there is no terms, right? So xk is going to look like this, right? We can always make a RKK. RKK is greater than or equals to 0. If RKK is smaller than 0, multiply both RKK and UK by just negative 1. So we can always make the RKK as greater and equals to 0. Then using this linear combination representation, we can construct RK, the case columns of R, this one, RK, so arbitrary column vector, RK, which is defined as a RKC equals to RK1, RKK, and 0, 0, 0 from here. In other words, XK is equal to RK 아니죠? U1, U2, UN times RK. 그렇죠? RK는 so RKs consist of the weight for the linear combination of the U1 and U2 and UK for the mate vector XK. In other words, XK is equal to QRK, 그렇죠? We discussed here, which is Q, 그렇죠? Which is Q. XK is equal to Q times RK for the K is equal to 1 to the N. Then let R, matrix R, is equal to R1, R2, and Rn. Then matrix A, X1, Xn can be the Q times R1, Q times Rn. X1 is equal to QR1, Xn is equal to QRn. So A is equal to QR1, blah, 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 QRn, which is equal to Q times R. Well, when R is defined R1, R2, and Rn. That's the QR factorization. A is equal to QR. The fact that R is invertible follows easily from the fact that columns of matrix A are linearly independent. Because the columns of matrix A are linearly independent, we can easily say that matrix R is invertible. Since R is clearly upper triangular and invertible, diagonal entries RKK should be non-zero because the by the 뭐예요? 여기 뭐였죠 우리? 인버터 매트릭스 theorem. 인버터 매트릭스 theorem에 의해서 it has the NP position, so RK should be non-zero. So by combining this with the fact that RKK is greater and equals to 0, RKK must be the positive. If not, we can make this one by multiplying negative value, negative 1 to the U1, UK. So then we finally achieve the Q and R, which satisfy these properties. This is a QR factorization. Question. 자, 우리 한 번만 더 설명할게요. 한국말로 한번 설명할게요. 좀 중요하니까. 그래서 이제 우리가 중간고사에서 배웠던 것 중에 LU 팩토라이제이션을 먼저 배웠었어요. 그래서 LU 팩토라이제이션이 사실 그 악셀러레이션 할 수 있고 인버스 매트릭스를 찾지 않고 악셀러레이션 할 수 있고 뭐 많은 장점들이 있어서 LU 팩토라이제이션 배웠었고, 이제 오늘 우리가 그람 슈미스 프로세스까지 열심히 배워오고 두 번째 이제 배울 이번 학기 두 번째 배울 팩토라이제이션 결국 이제 이러한 QR 팩토라이제이션이라는 거였어요. 그렇죠? 그래서 QR 팩토라이제이션이라는 걸 배우기 전에 이제 이게 어디에 쓰일 수 있는지는 우리가 이제 다음 시간에 얘기하기로 하고, 이 QR 팩토라이제이션이 뭔지 그리고 이걸 어떻게 디라이브 하는지를 얘기해보자라는 거였어요. 그렇죠? 그 QR 팩토라이제이션 가정은 arbitrary matrix A가 아니라 A가 n by n matrix인데 일단 리니어 인디펜던트 컬럼스를 가진다라고 가정은 할 거예요. 그래서 then A가 이런 경우에는 A는 Q 곱하기 R로 디컴포즈 될 수 있는데 이때 Q는 n by n matrix whose columns form a orthogonal basis. orthonormal basis. 그래서 orthonormal basis를 가지는 컬럼 스페이스의 올소널 베이시스를 가지는 벡터들로 컬럼 벡터가 이루어진 게 K이고, R은 n by n 어퍼 트라이앵글 매트릭스인데 인버터 매트릭스이고, 파티티브 엔트리들이 이츠 올소고널, 이츠 다이고널을 가지는 이러한 두 개의 QR로 분리될 수 있다라고 하는 게 QR 팩토라이제이션, QR 팩토라이제이션이에요. 그래서 이제 첫 번째 이러한 QR 팩토라이제이션이 정말 맞느냐, 즉, 어이구, 죄송합니다. 다시 공유할게요. QR 팩토라이제이션이 이제 정말 존재하느냐는 결국에 스텝 1, 2를 거치면서 진짜 Q와 R을 한번 구해보자라는 거죠. 저걸 만족하는. 저걸 만족하는 Q와 R이 있으면 QR 팩토라이즈 된다는 거죠. 그렇죠? 그래서 Q라고 한 걸 자세히 보니까 결국에 컬럼스 오브 매트릭스 A가 컬럼스 오브 매트릭스 A가 어떤 컬럼 스페이스 A의 베이시스였는데, 왜냐하면 벌써 그들은 리니어 인디펜던트하니까 그냥 컬럼 벡터 자체가 베이시스였으니, 그 말은 뭐냐, 이 컬럼 스페이스 A의 올스몰 베이시스 찾는 거는 X 벡터, 그러니까 셋 오브 디 벡터 X부터 이 올스몰 베이시스를 찾는 과정이더라. 그래서 Q라는 매트릭스 이렇게 만들 수 있더라 라는 거였고, 이걸 어떻게 하느냐? 그램 슈미스 프로세스 우리가 배웠던 걸로 하면 이걸 찾을 수 있겠다라는 거죠. 이 과정에서 R이라고 하는 결국에 뭐냐면, 여기서부터 보는 게 편할 것 같은데, 이 R을 그냥 먼저 곱해보면 벡터 각각의 컬럼 벡터 XK는 Q의 어떤 RK를 곱하는 형태로 표현될 수 있는 거고, 각각의 XK는, 그 말은 뭐냐, 이렇게 U를 가지고 리니어 컨비네이션을 통해서 XK를 만들 수 있을 때, 그때 리니어 컨비네이션 R이라고 하는 거를 우리가 벡터로 RK로 표현할 수 있다라는 거죠. 그렇죠? 그러면 이제 이거를 쭉 모아놓으면 이렇게 R이라고 하는 벡터가 매트릭스가 나온 거, 그게 결국에 QR이 되더라라는 거죠. 뭐 하나 다시 한번 그려보면 결국에 the R1 should be non-zero value and zero transpose, and R2 should be non-zero value or arbitrary value and zero transpose, and blah blah blah. RK should be blah 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 phi k times and zero transpose. So this is the shape of the vector RK. By considering all the vector RK, we can build matrix R. Finally, matrix A can be factorized to Q and R. This is the QR factorization. 그래서 이렇게 Q와 R로 표현할 수가 있다. 즉 다시 얘기하면 이런 리니어 인디펜던트한 커먼 벡터를 가진 매트릭스 A는 이런 형태를 가진 Q와 R로 분리될 수가 있더라 라는 얘기를 한 거예요. 알겠죠? Question. No? 질문? 마지막. Last question. No? Okay. So that's it. So okay. So today we will finish today here, and next Thursday we will see how to apply characterization for the arbitrary matrix A. So we will see the example for the characterization, and let's talk about meaning of this characterization and where this characterization can be used. Okay. No more question? So first of all, QR이 존재하려면 M이 M과 M이 N보다 크거나 같은 조건이 성립해야 되는 것이 없어요. 그럴 필요 없고요. 여기서 arbitrary M과 N 사이즈에 따라 달라질 수 있다 라고 하는 거고요. Question, 효린. So the finalism, data of finalism, not decided yet. So I can't decide the final exam date. So maybe computer science department will organize this. So I will let you know as soon as possible. But the final exam not yet decided. Okay. Any other question? 효리한테 제가 메일 봤어요. 메일 봤는데 조금 확인해보고 알려줄게요. 알겠죠? 네, 오케이. 서연 학생, 너무너무 좋은 질문이고 너무너무 어드밴스한 질문이네요. 요건 다음 시간에 얘기해 줄게요. 알겠죠? existence와 uniqueness에 관한 얘기겠죠? 네, 해줄게요. 정학생 질문이 컬럼 벡터 리니어 인디펜던트에서 m이 m보다 크면 인디펜던스가 성립하지 않은 거 증가해서 질문 드렸습니다. 그럴 수도 있겠네요. 정학생 컬럼 벡터가 리니어 인디펜던트 하려면 m by n이 인디펜던스가 m이 m보다 작으면 인디펜던스가 성립하지 않은 경우가 있을 수도 있지만 사실 항상 그렇진 않죠. 그렇죠? 잠깐만, 항상 그렇나? 항상 그렇지 않죠? 항상 그러나? 정학생 요거 제가 확인해가지고 다음 시간에 알려줄게요. 그럴 수도 있을 것 같은데? 그러네요. 요거 한 번만 더 확인해서 알려줄게요. 네. Other question? No. Okay, so that's it. So this is the end of this lecture. Thank you very much. And I just heard that this week is a festival, right? So most of you are freshmen, right? So please enjoy your enjoy festival and the first festival, maybe your first time. For the 20학번 친구들도 그쵸? 20학번 친구는 아마 첫 번째 페스티벌일 텐데 please enjoy. And I just heard that computer science department will have 영어로 뭐라 하지? 주점 그쵸? 있다고 하던데 뭐 관심 있는 친구들 한번 가봐도 좋겠고요. 저도 잠깐 내일 가려고 하는데 혹시 가면은 좀 보면 좋겠네요. 알겠죠? 너무 오늘 고생했고 우리 몇 주 안 남았네요. 이제 그쵸? 이제 저랑 볼 시간이 얼굴만 보여줘야겠구나. 이제 우리 같이 볼 시간 해봤자 봅시다. 3주 남았나? 3주도 안 남았어요. 그쵸? 그래서 이제 여러분 조금만 더 고생해가지고 잘 학기 마무리 하는 걸로 하고 우리는 마지막까지 힘을 내봅시다. 알겠죠? 정학생 너무너무 좋은 질문 줬고 제가 한 번만 더 확인해서 알려줄게요. 알겠죠? No more question? Okay, so that's it. So this is here. Okay, so this is end of today's lecture and thank you very much and see you maybe Thursday. Okay? 여러분 너무너무 고생했고요. 우리 목요일날 수업이 있을 건데 아마 여러분들 조금 어수선할 수도 있어서 제가 녹화로 대신할까 생각은 하고 있어요. 여러분들 혹시 이제 첫 축제고 아마 혹시 집행반 친구들 바쁠 수도 있을 것 같아서 녹화로 대신할 수도 있을 것 같은데 공지해 줄게요. 그래서 보도록 하고 우리는 다음 시간에 보도록 합시다. 그럼 너무 고생하셨고요. 우리는 다음 시간에 보겠습니다. 고생하셨습니다.